Let's go over activity number 3. The first two problems are for the section number 4 separable equation. So if you look at the equation here, it is e to the t divided by e to the x, or you could have said multiplied by e to the negative x. And also there's an initial condition given. So if you are not super comfortable with the variable here, you could have changed it systematically into something that you feel comfortable with. So it's e to the x, e to the negative y, and y0 is ln2. So it's up to you, but let's continue solving that problem. We want to put all the x term to one side, and we want to put all the e term to the same side. So what I end up with is to integrate them. So integrate e to the x dx and then e to the t dt. So we end up with e to the x is e to the d plus c. Well, the problem says when the t value is 0, I would be having the x value being ln2, so I have 2 equals 1 plus c, so I end up with 1 equals c. My final answer could have been e to the x equals e to the t plus 1, but you may also say I prefer to write my solution in terms of explicit form, so you end up with ln e to the t plus 1. So check what's my requirement. If I have said find xt, then you need to leave your solution in the appropriate structure. Otherwise, both will be treated as correct. So next problem we have is looks like this structure, and it's clearly first order. It is nonlinear. So unless I'm asking you to use some solving it graphically or solving by Euler's method, the only method we've learned is to use separation of variables for now. So we have x minus 4y fourth equals x cubed y squared minus 3 dy dx. So we want to shuffle things around and being able to separate the variable. So we have x minus 4 divided by x cubed dx y squared minus 3 y fourth dy, with the concern where y to the fourth could potentially be 0, so that's my other part of the potential solution. Don't forget, you may ask, why didn't I do this earlier? Well, don't forget exponential functions would never be 0, so I could have shuffled e to the x around, and technically I'm not even dividing and multiply e to the x to both sides, which is non-zero, so I don't worry about the case of dividing or multiplying by 0. So let's continue our discussion. This is x to the power of negative 2 minus 4 x to the negative 3 dx. We have y to the negative 2 minus 3y to the negative 4, and then dy. If I had integrate both sides, then I end up with negative x to the negative 1 plus 2x to the negative 2. This is the antiderivative. If you are not sure about your answer, you may check it very quickly. So this is y negative y to the negative 1. And then we end up with plus y to the negative 3. And don't forget, you need to have the arbitrary constant plus c appear on one side of the equation. So once we have this, well, I don't really have an initial condition, so you may leave it like this, or you may rephrase it a little bit. You could have said your final answer is 1 over y cubed minus 1 over y equals c minus 1 over x plus 2 over x squared. And don't forget, there's another possibility. This one leads to y equals 0. If that's the case, your expression, the x minus 4 times y to the fourth, is supposed to be 0 minus x cubed y squared minus 3, which is 0 squared minus 3, but y prime is 0, hence this is 0, it equals 0. So that's also a solution. So you technically have two different solutions. So bottom line, when you try to divide or multiply the same term on both sides of a separable equation, be careful whether you could have multiplied or divided by a 0 term, which may potentially lead to another answer. So the next two problems, always classify them first order, right? It's clearly linear, and it's ordinary differential equation. you could have discussed whether I can separate it or not, but for first order linear ordinary differential equation, we have a standard idea, which is integrating factor method. So we're going to begin by changing it into a standard form, finding the integrating factor, and then move from that. So this is dy over dx plus 2xy equals 3x, where you know your coefficient is 2x. Then your integrating factor is e to the integration of 2x, which is e to the x squared. So you multiply this term to both sides, which is, if I write it out explicitly, it's e to the x squared multiply y taking derivative on the left, 3x e to the x squared on the right. Therefore, I can integrate both sides, so it's e to the x squared times y, integrate 3x times e to the x squared dx. If you had called x squared to be w, then you have 2x dx to be w, my bad, to be dw, right? So x dx is 1/2 dw. So you can get to your original problem as 3 times integrate e to the w and then 1/2 dw, which is 3 over 2 e to the w plus c, which is 2/3 e to the x squared plus c. Therefore, you end up with your final answer, which is y, and then e to the negative x squared multiplied by 3 over 2 e to the x squared plus c, which is 3 over 2 plus c divided by e to the x squared, which is supposed to be your final answer. So this is what I end up with. Okay, so along the same line of thinking, if we look at the next problem, clearly it has initial condition, it's first order, it's linear, ordinary differential equation, so we can try to do the same thing. I have dy over dx plus 4x over x squared plus 1 y, which equals x over x squared plus 1. So we want to find our integrating factor, where I have integrate, where we have 4x over x squared plus 1 dx to be my integrating factor. If I had did the same thing, w is x squared plus 1, then dw is 2x dx. Therefore, 4x dx technically is 2dw. So my problem could have been phrased as 2dw over w, which is mathematically equivalent to twice of ln w, right? So I could have said it's twice of ln of x squared plus 1. So my left side of the expression is twice of ln x squared plus 1, and then multiply by my y, which is the same as x times ln of x squared plus 1 divided by x squared plus 1. So what I can do is, well, this is the derivative of that term, so all I need to do is integrate the right side twice of ln x squared plus 1 times 1, which is the antiderivative of x times ln of x squared plus 1 divided by x squared plus 1 dx. Well, it's relatively intuitive for me that ln of x squared plus 1 is 1 over x squared plus 1 times some derivative of x squared plus 1, which looks a lot like what's left. So I can use the separation of variable methods again. So what I'm going to do is I'm going to call my m as ln of x squared plus 1. So dm is 1 over x squared plus 1 times 2x times dx. I could have get rid of the 2 to the other side, so it's 1/2. So what I end up with is my problem is mathematically equivalent to 1/2 dm and then another m, which came from that. So just to clarify, this is my m repeated, and this divided by that times that is mathematically equivalent to those two terms. So what I end up with is 1/2 and then m squared, actually 1/2 of 1/2 m squared. So it is that plus c, and therefore it's 1/4 of what's my m? It's ln of x squared plus 1 squared plus c. So eventually my final answer is to get rid of the extra coefficient in the front. So what I end up with is going to be 1 over 8 times ln x squared plus 1 plus c, well, divided by 2 doesn't really matter that much, divided by ln of x squared plus 1. You know, an arbitrary number divided by 2 is still an arbitrary number, so that's why you didn't see me keeping the 2 back here, because it doesn't really make any difference. So this is my final answer. My bad, I should have taken my word back. I also have an initial condition y2 equals 1. So let's try to plug it back. So y2 equals 1 means y value is 1, which is 1/2, which is ln, which is 2 squared plus 1, plus c over ln of 2 squared plus 1. So 1 is 1 over 8 times ln 5 plus c divided by ln 5. So I have 1 minus ln 5 over 8 times ln 5 equals c. So c is ln 5 minus ln 5 squared over 8. So your final answer is to have the c plugged back into it. So that is supposed to be my final answer. We hope this addresses all your concerns. Well, technically I should have copy pasted and rewrite my answer. So let's put it down here and rephrase my c, which is ln 5 minus ln 5 squared over 8. And here's our final answer. Okay, so that's it.